Okay, this is shear example 4. And this is going to be continued, and this one is going to be page 6. So this is going to be the same calculation as the one we did before in order to calculate the demand on each weld, which previously we worked out to be 1.19. But in this case here we're going to be using the equation for the shear flow, and the equation for the shear flow is going to be Q, which is the shear flow is going to be, so we're going to be using this expression, Q for the shear flow is going to be equal to, maybe I should put that Q as a function of Y, as the shear flow is going to be equal to V times S dash as a function of Y divided by I. And if you remember from the other expression that we had, the other one was tau, the shear as a function of Y is equal to V S dash as a function of Y divided by I times B as a function of Y. So we can see there that Q as a function of Y is equal to this portion, so that is equal to Q as a function of Y divided by B as a function of Y. So the units of that, since that is in units of newtons per millimeter squared, and we can see that the units of Q are going to be the shear multiplied by the dimension of breadth. So the dimension of Q, which is the shear flow, is going to be newtons per millimeter, since we have eliminated this portion here by taking it outside. B as a function of Y, which had its units in millimeters. And later on we're actually going to express that in terms of kilonewtons per millimeter, but that doesn't matter, that's just the dimensions. So let's have a look as to why this is useful. Let's take a simply supported beam with a load at the center, and that's going to be 3500 in order to arrive at 1750 kilonewtons on both sides. So if we drew that out as a solid, so just taking artistic license at the time being, so we draw that out, and then we've got our load of 1750 kilonewtons coming up there. Now that, obviously in a free body diagram, ignoring bending, must be equal to the shear force coming down, and by complementary shear stresses there needs to be a shear stress acting there. So that's what I said by artistic license, because you could tell me that there's going to be no shear stress acting on the top surface, since it must be zero. Now if we had, let's say, had another block to the right, then that bit there would need to have equal and opposite shears, and that one is going like there, and that one is going on that side there. And then if we had another bit going up to just before where the load is being applied, so we would assume that this 3500 kilonewtons is being applied shortly after, so it doesn't get in the way. Then up here on this face here, that shear stress must be acting in that direction. There's a shear stress there, and then there would be a shear stress down across that surface. So if that's 1750 for equilibrium, so 1750, then that shear stress must also be 1750, and then both of these must also be 1750 as a summation of a force. And if you're wondering about the direction of the shear stresses on the bottom and top faces, that's as a result of complementary shear stresses, which we covered in CIV 210. Now let's separate this. So let's just separate that all out. So just for argument's sake, we'll say that's where the cuts are going to be taken. So then, so that bit there is going to be that portion there where some cuts have been made. Now, if we drew the free body diagram, so let's just follow that up. So if we drew the shear force diagram, we would draw the shear force diagram something like there, so it's going to be 0 at the center, and then come back to 0 at the ends, and then these peak values are going to be these values are going to be 1750 kilonewtons. Now what happens in our case, where we have this cross section? So let's try and draw that out a bit bigger. Let's do it there. So we've got the metal plate at the top, and then we've got this sliver which is going to turn into our weld, and then down here we've got the main sections, which are going to comprise of our welds at the top and bottom, so that's going to be the web, and then we've got this little slither up there which is going to be the weld, and then at the bottom up there we are going to have our our plates. So there must clearly be a shear force or a shear stress going up, so I'll just draw it getting gradually smaller and smaller, and then up here there would be a shear stress as well, although it's going to be 0 at the bottoms, and along here, I'll just draw it in solid, we would have so that's how it's that's how that bit that I've drawn in a circle is going to look, and then that bit down there would be a force going down, and then there would be a force going down there. So let's now, if we now considered the stresses acting on the top and bottom surface, so we know that it's going to be 0 at the top surface, so I'll leave that out. So we're going to have something along there, and then we're going to have something along here. Now for the weld, which is going to be carrying the shear of 1750 from the shear force diagram, there would therefore need to be some sort of shear stress going up and then down and then up and then down and then across there and then across there. So there's going to be some sort of distortion in shear, and that distortion in shear, I'll just try and draw that up here. That distortion in shear should probably look something like that. And you can see that the direction of the stresses for the welds are exactly the same. So up there, that would be the weld. I'll consider that to be the weld, and then I would call that the web, and then I will call that the flange, and then up here at the bottom also the flange. So I've drawn the shear stresses. Now if we look at the equation, so let's just define our coordinate system, the y going up there for argument's sake. So small q, which is the shear flow as a function of y, is going to be equal to the shear force times s dash of y divided by I. So we can calculate the value of the traction. So that would be, we'll call that the traction. So that value of the traction can be calculated being q as a function of y is equal to v times s dash as a function of y and divided by I. And in this case, because it's up there, y is going to be equal to 280 millimeters. So that's going to be 280 millimeters. And then that y there is going to be 280 millimeters. So now, in the previous page we've already calculated our I. So our I came up as our I was 1.361. Yes, I'm doing a recording. I don't want it to. So that's going to be 1.361 times 10 to the 9 millimeters to the fourth, and then we had actually calculated that before, and that worked out to be 1.74 times 10 to the 6. And that was going to have units of millimeters cubed. So the value at 280 millimeters up worked out to be 2.238. kilonewtons per meter. So that's why it's useful, because in this we haven't considered the cross section at all, and what it's telling us is that if we draw out the beam again, so let's draw out the beam again. So that's going to be the beam, and then this time here, I think I'll just ignore showing the weld. So we've got the web, and then we've got the top and bottom flange, and that's telling us that. Let's draw out this portion here as well. We've got a combined shear force acting downwards, I suppose. So let's deal in terms of forces. Why not? So from equilibrium, we've got a shear force of 1750 kilonewtons, and then on the other side we've also have a combined shear force, which is then distributed into shear stresses, tau, for which the variation is going to look something like that. So that's going to be the variation of the shear stress, and the maximum shear stress which we calculated was going to be 143.64. If you remembered. And then there would be another shear force coming up there from 0 up there for the flange. So that we'll call the flange, that we'll call the web, and that we'll call the flange. So just trying to separate them out, and then obviously the value goes to 0 at the tops. So those values there are 0. So we've got for our equilibrium, we've got 1750 downwards to the left, and also 1750, which has to be equal and opposite on the other side. Now we also have some traction which acts in this direction on this face here. And also, of course, it has to continue off on this face here. So it's easier. You could sum the whole force if you wanted to, but it's easier to give it in terms of Q, in terms of units of kilonewtons per millimeter. And Q acts horizontally, and on the other surface at the bottom of the flange it also acts in that direction for the complementary shear stresses. So we've got this force in terms of units of kilonewtons per millimeter, which we can calculate, and you can see it has nothing to do with B. And Q acts horizontally along the length of the beam. So Q is a force that has, maybe I'll just draw it along there, although I should have drawn it a lot smaller. So Q is a force that acts along there, and also acts along there, and it has its units in terms of kilonewtons per meter or kilonewtons per millimeter, and that's measured along the length of the beam. So why is it useful? It's useful because it's completely ignored the cross section. So now we draw the cross section of the beam. So I'm drawing the cross section out here, and it tells you that into the page, i.e. in the direction into the page, so if we assume that coming out of the page is going back to the support, there is this traction Q coming at you, and also on that surface there would be another traction Q acting there. So, and that traction Q is going to be equal to 2.238 kilonewtons per millimeter. Kilonewtons per millimeter. So that should have been millimeters up there. So just to re-emphasize, Q runs into the page as you look in the cross section or along the length of the beam. So if we know our value of Q, which we have calculated, then if we want to work out the demand on each weld, so we can see that there are two welds up here. Then let's write here demand on each weld is equal to 2.238 kilonewtons per millimeter. So along each millimeter length of the beam, so let's just assume that the beam's acting in the x direction, so along each millimeter along the length of the beam, there would be a 2.238 kilonewton per meter, this force Q here, or shown here. And in this case, because there are two webs, we need to divide that by 2 because it's per weld. So we've got a shear flow of 2.238 kilonewtons per meter, and that translates, when you divide it into 2, to become 1.119 kilonewtons per millimeter. So you could have done it as we did before, going back to working out tau y, bringing in the by and then removing the by when you wanted to work out the demand per weld, but since that one is just removes each, you're just doing work for nothing, because you've got the by, and you might as well ignore the by and calculate Q directly, which is what you want for the weld. So we would then say that each weld in the horizontal direction along the length of the beam needs to take a traction or a shear force measured in terms of kilonewtons per millimeter of 1.119 kilonewtons per millimeter, which is exactly what we had calculated. Before, except that I probably missed out a 1 on the 0.119 kilonewtons per millimeter.